We see that the foundation of today's artificial intelligence today is precisely neural networks. And neural networks are a computing paradigm, a way of using computers that is completely different from how we have been accustomed to thinking. Well, then let's start with a basic problem, an example problem. And let's look at these Zener cards. They are 5 cards used in psychological investigations. Recognizing one card from another could be a very simple job for a computer, right? If I have a sequence of cards, how are these jobs normally set up? Let's move on. If I can number each card, I can number it and associate a number, specifically a symbol, a number to what we are doing. It is then very easy to recognize one card from another based on the numerical value. But there is a significant problem. I can only do this having already fully formalized the problem, that is, having associated a specific little number to each element. I then perform the search process on a code that I have built from scratch. If I want to start from raw data, that is from the image, how can I recognize the image? At this point, the problem becomes graphical. Let's see a little bit what that means. I need to distinguish one of these images from the other. It is relatively simple if I work on these fixed images here. It is relatively simple to learn the functioning pixel by pixel and catalog each image by working pixel by pixel. But do you see what happens? I can try overlapping the images. I can try on each one of these. At a certain point, I find an image that overlaps with the one I am looking for. And so, well, I have found what I need. Okay? The problem is thus approached in a deterministic way. It is still possible to use the computer as we know it, that is, with loops, with everything we need. But let's look at what happens. I'll move this over here for a moment. I don't know if you can see it. Let's look at what happens when I instead make some changes to the real images. It's not like the images are perfectly framed. These effects exist. Rotation, translation, scaling, because, for example, the camera has moved further away or closer. Well, if I want to use this approach, recognizing a graph also, it becomes absolutely impossible. It's a complex problem. I mean, the number of tests I would have to run becomes extremely heavy, and therefore it's not possible to use. So pixel by pixel comparison has a reasonable computational cost when it's done on fixed images. If I propose these possibilities for change, so real images, think about something that has become normal today. But when I did these things, it wasn't normal at all. Facial recognition at the airport, for example, from a camera, right? So the face isn't necessarily always in the same mode, it's not like I'm working on fixed images like those on ID cards where essentially the images are fixed. So it's easier to make the comparison. I am using real images. That's why the deterministic approach doesn't work. What is the deterministic approach? It's a consequence of the architectures you are studying, for example, in systems. The von Neumann architecture, for example, we have a single, let's say, processor connected to a memory, a control unit with some input-output devices. This is the computer architecture. From this architecture, it is natural to derive a deterministic approach. Do we understand? The computing power we need is not sufficient. Even if we were to succeed, we are somehow wasting our energy as well, and also the electrical energy we use. We are wasting it because that is not how it is worth addressing that problem. A completely different approach is needed. So let's go see how it works. The software we are used to using is an approach, let's say, that is always deterministic. It is software that takes the form of an imperative paradigm. That is, we command the computer based on some instructions we have, and so we tell the computer exactly how to tackle a problem. For example, if I have to calculate the perimeter of a triangle starting from the length of the sides, I have to do the sum, and this is something that can be done. We can use the flowchart as a graphical and therefore also conceptual representation of what we have to do and what we can do with the imperative paradigm. Let's start looking at something that is different instead. It was the approach of artificial intelligence in the early days of artificial intelligence, which was in the 80s, 90s, like that. Even earlier, I must say, actually, yeah. But in the 80s, 90s, there were There were some first results, and so there was also this possibility. How does the expert systems approach work? I'm showing you this also because despite 30, 40, 50 years having passed, we shouldn't go back to these things. In computer science, it has happened that topics that were set aside then came back into fashion later. The same thing happened to neural networks too, right? You have read about the famous AI winter. So how does an expert system work? It is coded programming, but of a different kind. There are facts and rules. I'll give you an example. The facts could be the direct flight connections that exist between two cities. The rule in this case, what could it be? The fact that if there is a direct connection, for example, between Catania and Milan, then there is a direct connection between Milan and Brussels. Well, I'm giving an international example. It's not, let's say, represented here in the image. If the times are correct in the sense that, for example, the first plane arrives and then the other one departs within 2 hours. All right, that works. And now you can create a rule saying that the Catania-Brussels flight is created by combining the two flights, Catania-Milan and Milan-Brussels, if the rule regarding arrival times is met. Is that okay? This is the so-called expert systems approach. And mind you, they weren't all negative. In the field of medicine, for example, expert systems worked quite well in the early years. Now, they have been set aside a bit because writing rules let's say, for very complicated situations is not easy. They are quite limited. You understand that it is not very intelligent to define the fact that there is one flight and then another flight, and they are put together to form a connection. Yes, it's something, let's say, that the computer does automatically, but it's not very intelligent. So here is a different approach instead. It's called connectionism. There, the neural networks that, if you want to define them in a more generic way, are called connectionism. And where does the idea come from? Here, I'll show you two images. One is an image of a brain, of the neurons of a human brain, and the other instead is an image of illuminated cities. The network of one image, the network of the other image have some similarities. The important thing in this approach, we will see it immediately, is not what we can do with a single computing node, but the fact that there are so many computing nodes connected together, a bit like what happens with cities. So let's see how the central nervous system works. Let's say, obviously, in a very quick way. A cell is formed by the nucleus, then it has protrusions that serve as input signals. To carry the input signals and an output, that will then be the one that carries the output signal. But be careful, the output is not unique, it branches out, and therefore it is connected with hundreds of other neurons. To get an idea of the number of neurons we have in our brain, we see that there are normally 10 to the 11th power, 100 billion neurons. The number of connections for each one is on average 100. So the 100 billion neurons give rise to 10,000 billion connections. It's crazy, and it's all in here, eh? The fundamental idea behind neural networks is to train the computer to reason and process information in a way that mimics the human brain. Exactly how this complex system actually does it in practice. Okay, so let's see how this perceptron works. What is the perceptron? It is the artificial equivalent of a natural neuron. It has the same type of reasoning. Okay, so how does it actually work? Well, there is an input connection that is weighted. Essentially, the signal coming through that connection is multiplied by a small number. This number is normally set somewhere between 0 and 1, or sometimes between -1 and 1 to determine the strength of that input. One of the two, all right? You can choose one or the other interval. So I have an input that is normally also, let's say, chosen in the range always between -1 and 1 or 0 and 1. You decide how to work. It is multiplied by this weight, and at the output of the neuron, all these data are summed up. So it is a fairly simple calculation. After that, a transformation function is applied, as they say. Here, this function that I chose for the image is called a sigmoid, and it is a function, you see, that has the ability to attenuate extreme values. That is, for extreme values, the sigmoid then points it has two asymptotes. So even if the input becomes very strong, the output value is always the same. The problem with neural networks, obviously having many computing nodes, is stability. If we let the nodes be free to have any value they want, what can happen? We can have nodes that generate values that are too high. And so practically the system becomes unstable. It doesn't reach convergence. What does convergence consist of? That all neurons must have a regular output between 0 and 1. This sigmoid function ensures this because no matter how much I load the neuron's input with very high values, the output is always flat. So it cannot, let's say, do the so-called overshooting, that is, establish a value that is too strong. What is the effect of this neuron? If we map, that is, if we graphically present the input values, we have a region of input values that gives us a certain result and a region that gives us another result. Let's say that the neuron, thanks to the weights, introduces a mapping in the space of the input values. This is an approach that physicists, for example, use to describe physical systems. That is the configuration space, the phase space. It is something that, let's say, is widely used by physicists, but it is useful. You see, even between one subject and another, interesting ideas can be borrowed. This, I repeat, originated in the world of physics, but we will make, let's say, many considerations that have to do with physics. So what I told you, the inputs are weighted. The set of values determines the state of the network. Learning. What is truly revolutionary about this approach? That the program does not exist. What exists is the fact that for a certain phase called learning, I show examples and I show the results that I want with those examples. So, for instance, if I were to show you a specific example of an even number, and then I continue to show you many more examples of even numbers, I would explicitly tell you that those are indeed even numbers by fixing the output for you. This process helps clarify exactly what constitutes an even number through repeated guided observation. There is a mechanism at this point, the learning mechanism, that retroactively, by going back, works on the weights and adjusts them in order to reduce the error. By doing this operation on a large amount of data, what we get is that the network learns from that example and gives that result. I show you another example of a different type, and it gives me the other result that I associated with the other example, and so on. The network learns. Obviously, it's a very numerical way of learning. So if I, for example, show it an example that's halfway between two things, I might get an uncertain result. I mean, it's not the case with even and odd numbers, but it depends on what I want to achieve. Let's put it that way. So how does this learning mechanism work with backpropagation? That is, backpropagation is the method by which I provide values, I provide expected results, the so-called target, and then backpropagation adjusts the weights so that the network gets closer to that result. This is done not just for one example, it is done for thousands of examples. If you remember, I told you I tried to teach the geometry of the regions of Italy to the neural network. That is, I showed it some municipalities. I gave the coordinates of the municipalities, and I said, however, which region they belong to. This was for a certain number of municipalities, for example, 1,000 municipalities. After I did this training, I showed it other data without saying which region they belonged to, and the neural network was able to recognize them. Then, when I finish the recording, I'll show you an example of this. So let's move on. Here is what a complex neural network looks like at first glance. There are neurons, let's call them that. They are called perceptrons or nodes, more generically, input nodes to which the data arrives. Normally, a network like this one, a fully connected network, there are all possible connections. There is a hidden layer. Well, let's jump ahead. This work is from 2009. What do we have today? Many more hidden layers, deep learning. Why deep? Why profound? Because there are very many hidden layers, so the ability to memorize, generalize, and abstract is a much stronger capability today. In this, however, what is let's say, the point? That it doesn't exactly learn what I say, it learns in an imprecise way. It learns in a nuanced way. It actually learns how it works. It learns to do something that resembles it. It resembles it exactly. It's not precise. But in the meantime, it generalizes. If I show it something similar, it reconstructs. Look, I don't know if I'll talk about this. Yes, I'll talk about it later, so I won't give it away now. Yes, it was there. I remember this. Now we'll talk about it later. So transformation functions are very important in network management. So you see that it becomes a mathematical problem of stability. The linear function, very simple because you don't have to do anything, is a transformation that leaves it identical, but it doesn't guarantee stability. The threshold function, the step function, the sigmoid, which can be like this, it can also be between -1 and 1, is actually the one that is used the most because it is the best. Depending on the interval chosen for the initial data, or 0, 1, or -1, 1, different forms of the sigmoid are used. But this is the best solution. That is, practically in the end, it always brings the network output back to between -1 and 1. Let's move on. There are other possibilities. For example, the Gaussian. This one you see is a two-dimensional Gaussian surface. It can also be used to approach other problems. All right, let's move on. How does the network work? It uses something called gradient descent. In reality, when we give it an example, we find ourselves at a point on this surface. The problem is defined by this surface, meaning that as we move along this surface, we try to reduce the error. We need to try to descend as much as possible. However, if we look at this surface, it has some pits, let's call them that, some holes, but it's not like we can necessarily reach zero, meaning the error won't necessarily be zero. Especially the algorithm I am using, the gradient descent one used in backpropagation, brings me to the nearest minimum. It's not necessarily the lowest minimum. You see this minimum here at practically zero, it's flat because let's say the function cannot go below zero. This minimum here is a dip, but it's not zero. Now, it depends on the complexity of the problem. If I want to recognize, for example, people's faces, this is a fairly complex problem that has many of these dips, and therefore it is not certain that I will be able to find the best solution. Regarding this issue of local minima, the algorithm that is used is an algorithm that is subject to the problem of local minima. Because, for example, it's a tricky thing. If there are two particular faces, it could get confused. Yes, if there are two similar faces, it means there are two very close minima, and so it can easily fall into the wrong one. There are techniques, but just to tell you about shaking, shaking is a technique that comes from physics, specifically from solid-state physics. They discovered that some crystals, not a physical shaking, it's a heating that is applied to shake the atoms a little bit. Sometimes it happens that the atoms then move into a more stable situation, that is, into a lower energy minimum. This technique, in which in jargon is called annealing in English, is also used with neural networks. You see that, but what does that have to do with it? Mathematics, and we'll see later next year, mathematics unites all these things we are doing. And so sometimes the mathematics is the same even for very different problems, and the solutions can also be the same. A digression. Networks can be used. The ones I told you about are the so-called backpropagation or feed-forward networks. They are similar, let's say, then we need to go into a bit more detail to understand the difference. There are networks that are used for other things, for example, for memorizing, right? Which have different characteristics compared to the memories we use. For example, Hopfield networks are objects that store data by spreading it across the entire network. That is, it's not like the memory we have in our computers. Imagine that I puncture a point in the memory. I have ruined a specific piece of data. I have lost that data completely, right? If I have ruined, or more normally, if a chip is erased, very often the memory is also divided across multiple chips, so that data was localized in that chip, and I have lost it completely. The other data is not damaged. With Hopfield memory, something different happens. The data is spread throughout the entire memory and when it is reconstructed, it is retrieved from the entire memory. What is the advantage of this system? If it gets damaged, all the data will be slightly damaged, but possibly, if the network is well made, the value can still be reconstructed. So if a part of the memory is damaged, so-called distributed memories of a distributed type with various things I won't go into, well, they are, among other things, completely connected. The memories used for face recognition, just to give you some names that might be useful, They often use a competitive architecture like this one by Kohonen-Grossberg. What does that mean? That the nodes are all connected to each other and they work by selecting the winning node, meaning the node that has a value even slightly larger wins it all. And this is used for selection. If I need to perform a classification into a single class like face recognition, it has to tell me that person. If I want a single output, then I have a competitive layer of this kind so that the node that is closest to the solution is further reinforced, wins, and prevails over the others. So this is one application. Often it can also be done with traditional techniques, but it can be done with neural techniques. This is a possibility. So let's look at the applications. A historical thing that has existed for ages, handwritten character recognition. How does it happen? Here is a more specific example. It becomes pixelated, as they say in jargon, meaning the image is divided into pixels and a threshold is applied so that the 3 becomes this pixelated image you see on the far right. No, the one in the center. And obviously then it's the ability to recognize the 3 compared to the 2 compared to the 1, because for some pixels it is more likely that they are lit up with the 3 compared to the 2. If I look at the entire quantity, then what is it that I get from the neural network? This is 79% of 3, 42% of 5. It connects the possible outputs, the probability there. This is called, and here there is studying to be done, the Bayes approach, Bayesian statistics. That is, it's a way to evaluate the possible classifications, the one that has the highest probability, okay? And the neural network also functions as a Parson-Bayes classifier when then you see, let's say, it establishes the probability that it is this, that other, that other, that other. Think about a disease diagnosis. I have these symptoms. What does the system answer me? Before there were expert systems, but now how do neural systems respond? At 35% is a bit low. At 35%, it's this disease. At 28%, it's this one. At 15%, it's this other one. The doctor starts thinking about the one at 35%, starts looking at what tests we can do to determine if it's really this one, which can confirm this possibility for me. But it's not an absolute certainty, okay? It's this one, or it's this other one. Here it tells me this number is either 3 or 5 or 2. It won't be 1 because 1 is completely different and the probability that it is 1 is only 7%. We are finishing there are 2 or 3 slides left. How does it work for real images? So we saw this for images, for the handwritten characters, which is easy. In the end, it's easier. What if I have to study real images? Very well. I worked on these things. I was working in 1991. I did a job and certainly for back then it was very valid. Okay, I have to finish within 2 minutes, all right? Which was very valid. So let's see how this work functioned. These that you see, the famous orange, here we've arrived at the orange, were images of an orange treated with false colors. In order to distinguish, the ones on the left are of an orange, the ones on the right are also of an orange, but one that had a defect. These spots are defects, things that are not right. So it was necessary to establish a correspondence between a discrimination between this one and this one. How is it done? They established, this is the approach I used, masks that make me notice, let me go back if there are these radial structures. However, these masks are a bit heavy to use. They have to be tested on every point, on every pixel more or less. So various masks are tested. Well, it was 1991. Even if the approach is Zurdo's, it was still from 1991. In the end, this gave me an index. Then there were other simpler indices, right? For example, whether there were many colors or few colors. You see that here there are more colors, here there are fewer, and I put everything together. When I classified the image based on these criteria, the neural network helped me distinguish the images on the left. These ones here, let's say, which specifically concern the stem. Did you understand what the problem was? That is to have the oranges roll by and figure out if they were defective or not. Meaning, if this thing that was framed was the stem, it's normal for it to be there. Or was it a defect on the orange, like a bruise, a piece of hail that had hit the orange and left a spot? So how do you distinguish between this and that? Let's say I should have put in the image of a defective orange. It can be done. And the neural network, even back then with the resources of 91, managed to distinguish, getting only 3 out of 68 images wrong. It was able to distinguish and perform this simulation, meaning it was able to separate the two patterns like this. See? And this is something, nowadays these techniques are extremely more advanced, so they work much better. They can even recognize a face immediately. Everything we are able to do with artificial intelligence, chatbots, and all the things that exist now. All right. To see, well, because they were seeing through a computer, it shows us what they were seeing. Perfect. But they have a low world and it wasn't, oh well. Okay, let's stop the recording for now. So